6.6, improper integrals. I think this is the last section in chapter 6, right? Yeah, I think so. Chapter 6 has been quite an important chapter, applications of integrals. Okay, improper integrals. If something is improper, right? Like the dead ball was this weekend, right? Dead ball was this weekend. So what would be like something that's improper at a dead ball? Well, if you're an escort and you're standing up on stage and you're supposed to be acting proper and someone says the University of Texas and you go like this with a white glove, that would be improper, okay? It's not the time nor the place to be doing something like that, Tyler, okay, right? Or if you're in church and if you agree, you know, you say amen, right? That would be proper. But if you said F and A, right, that would be improper. Both ways show you agree, but one way is by F and A, I mean like factor A, right? That would be improper. So what makes an integral improper? Does it like eat with its hands with the wrong fork or put up the hook 'em horn symbol at a black tie affair? Or does it cuss in church? No. It's neither one of those. Now, this diagram right here, just, you know, this is good for like the rest of your life. If you never do improper integrals, there's a right way and a wrong way to pick up a box, a heavy box off the ground. This is actually two different people. So if you think about, first of all, how to pick up a box, the first guy is bending at the knees, which is how you're supposed to do it. It saves the back. The second guy is bending and hurting his back with the weight. He's going to hurt his back, throw his back out, and that's going to be more of a concern as you get older. You young people, you can throw your back out and whatever. The next day you're good to go. As you get older, it's kind of harder to recover. So in terms of lifting the box, the second way is improper. But in terms of how you want to line up to look at things, we could say the first guy got there first, so he has space in front of him. This guy's a little bit too close. He should have backed up a bit because now he's in an improper position because he has to, as Tyler said, stare at the other guy's derriere. Right, a little too close, right? A little too close. So what makes an integral improper? Well, we're going to discover that. Let's go to the calculator. You got a calculator? Pull it out. You need to come up here and borrow one. We're going to evaluate the integral of 1 over x from 1 to 100. Let's see what that is. Now, again, there's several ways to do it. I'm going to go to y1, and I'm just going to type in x to the negative first. You got a reciprocal button right there above the squared, if you choose to do it this way. And now I'll just go math 9. We're going from 1 to 100. And the function is in y1. So remember, that's alpha trace y1. And we're going with respect to x. So far, so good? So good so far? All right, we'll hit enter. Woo! Look at that. It's 4.6060 or 61? 605. Sweet. 3 decimal accuracy. If you only did 2 decimals, that wouldn't be a -1. That would be an x. It'd be incorrect. Okay, sweet. That is a fascinating number. Not really. It's not really that fascinating. Let's see what we're actually doing graphically. You know the graph of 1 over x, right? That's your rotated hyperbola. It looks like this. It has a vertical asymptote on the x-axis, on the y-axis, sorry, and a horizontal asymptote on the x-axis. And there's the other branch over. Yeah, and you can't see it, but there it is. There it is, right? You know what it looks like. So what we did is we just found the area under that curve from 1 to 100, which is this little piece. Let me make sure I have the right. Okay, that looks good. It's this little piece right here. So you could approximate that with a trapezoid if you wanted to, just by drawing a secant line. But there you go. The area of that is 4.605. Totally not fascinating, is it? We kind of take for granted now our ability to find areas under curves. All right, let's go to the next one. What's the integral from 1 to 1,000? Woo-wee! We are going out now further by a factor of 10. So second enter, or go up and grab it, or just type it in again. I'm just going to add another 0 to my upper limit of integration, and I hit graph like an idiot. I am an idiot, okay? I meant to hit, not graph, but help me out. Enter, yeah, enter. It's on the other end of the vertical keypad there. Oh, 6.907, and now I'm writing with a highlighter. And now you can't even see it. Yeah, okay. 6.907. All right, so if you look at the graph, all we did is we came out over here to 1,000, and we picked up a little bit more area. Now, what's happening to the graph as we go out further to the right with respect to the x-axis? It's approaching 0, okay? So as we go up further to the right, even by like a factor of 10, the area is getting smaller and smaller and smaller as we go to the right. So even though we're accumulating more area, we're accumulating area at a very decreasing rate, right? By less and less and less. Let's look at the last one here. Woo-wee! Jiminy crickets. We are now going out to 1 million. That's going to be more like over here. What do you expect it to be? Do you expect it to be bigger than 6.907? Yeah, barely bigger or tons bigger? We don't measure area in tons. I set you up for failure. I'm sorry. So if I want to go to 1 million, I have to add how many more zeros? 3. All right, now I hit enter. 13. Not quite doubled it. Not quite doubled it. Was that bigger or smaller than you anticipated? Yeah, it was bigger than I anticipated, right? Because we were accumulating area at a decreasing rate. If it's approaching 0, by the time we're out at 1 million, I mean, it's very hard to even see distance between the x-axis and the curve. Let's try one more, okay? Let's try one more. Second enter. Let's go out to past 1 million. What do you want to go? 1 billion? That's 3 more zeros. Now, remember, sometimes we could break the calculator. I didn't break it. We go out to 1 billion and we get 20. 20. So, again, not quite doubled it. Went out by a factor of 1,000, not quite doubled it. Okay, so we got 20 there. So, based on our values above and the extra one that we calculated, Tyler, you could text people about this later. Yeah. What do you think the integral is from 1 to not 10, not 100, not 1,000, not 1 million, not 1 billion, but to infinity of that equals? You think it's infinity? Infinity would not be a bad guess, right? Because if I do go out to infinity, is the graph ever going to touch the x-axis? No. So you can always say that as you go up further and further, even though it gets harder to see, you could have this magic power of being able to zoom in, and you'll always have a finite area there. So as you go up to the right, you're accumulating an infinite amount of area. It would kind of make sense that then the integral would equal infinity. Now, do our numbers support that? Are they increasing towards infinity? 4, 6.9, 13, 20? Yes, you should think infinity, because based on our experience in the past, if there was a limiting value, by the time we go from 1 million to 1 billion, we would already be kind of approaching it. You would see that those two numbers would be very, very close to each other and not getting further and further apart. So this is a very, very good guess. Now, we're going to verify this later. So what makes an integral improper? What's different about this integral from the ones we've seen? What? We're going from 1 to infinity. Yeah, I think I heard a mumble of something like that. When you have an infinity or a negative infinity as an upper or lower bound of your integration, either one, you're going to have one version of what we call an improper integral. So in this case, we're integrating up to a horizontal asymptote. Sometimes we might be integrating up to another discontinuity, a vertical asymptote. Now, we already talked about integrating up to holes and jumps. Those are going to be fine. If you ever have a hole or a jump, you're going to be able to find the finite area and use that to find the integral. But asymptotes are very, very different, because graphs can approach asymptotes at very, very different rates. 1 over x approaches the horizontal asymptote, relatively speaking, pretty lazily, right? It goes to the x-axis not very steep. When you compare it to like 1 over x squared or 1 over x cubed or 1 over x to the 4th, that's going to approach the x-axis a lot more quickly, all right? Speaking of something that might be going to the x-axis a little bit more quickly, let's look at e to the negative x. E to the negative x is your exponential function, e to the x, and what does the negative in front of the x do to the graph of any function? Reflects it across the y-axis, yeah. So that makes it an exponential decay function. It looks like that. So this one passes through the point 0, 1. So notice, very, very similarly, we have a graph that's approaching 0. But this one is approaching the x-axis at an exponential rate, whereas the other one was approaching it at essentially a linear rate, x, right? So this one's approaching the x-axis much more quickly. Do you think that's going to have any effect on, bless you, finding the area from 1 to larger and larger values of x? We're still going to have an infinitely unbounded region. Let's see what the numbers say. Let's go ahead and calculate the integral from 1 to 100 of e to the negative x. Now on this one, I'm not going to bother putting it in y1. I'm just going to go math 9, still starting at 1. We're going to go to 100 first, kind of keep it modest. And then e to the negative x, that's second ln to the negative x power with respect to x. Ooh, look at that. Kind of a small number, 0.0367. If you remember from above, we already had, starting at 1, 4.605. So you can already see the difference in how fast these two curves go to 0. By the time we get to 100 on here, we haven't even picked up half of a unit of area, whereas the one that went to 0 lazily, 1 over x, we already had more than 4.5 units of area. So it goes to the x-axis a lot more quickly. All right, let's see what happens at 1,000. So we'll just recall it. Scroll back up here, add another 0 to the end, and hit enter. Woo! Look at that. 0.367. What the? It looks like the same number all the way out to the end, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, to 10 decimals. It's already the same. Is that possible? I just opened iTunes instead of going to Reflector, just so you know. I'm an idiot today. All right, let's see. The first time I went out to 100, that would be this much, right? I just went out to 1,000. The graph tells us that the area that we're accumulating should be bigger, right? As we go out to 1,000, it should be bigger. Is it bigger? Yeah, it is going to be bigger, but it's going to be so much smaller bigger that we're not going to, is that the right way to say that? Yeah, it's going to be so much smaller bigger that we don't even see the increase up to the 10th decimal mark. But we still physically are adding more area. It's just so tiny, it's way past the 10th decimal place. All right, so what do you expect to happen if I went out, let me close iTunes. If I went out to, I don't know, let's just go out to, let's not go to 1 million. Let's go out to one more, 10,000. Oh my goodness gracious. That's your calculator's way of saying what? Really tiny, right? That's no longer 0.367. That's your calculator's way of saying, help me out, 0, right? That's your calculator's way of saying 0. That is a decimal with 16 zeros and then a 1. Is that the right answer? Is the answer 0? Should it be approaching 0? If you think about, again, the graph, is it possible that we start at 1 and as we go up further and further and further, we're approaching an area of 0? No way, no how. Okay, so we talked about this the other day. We just broke the calculator. And this is breaking the calculator and getting punched in the face. This is not breaking the calculator and having it give us the right answer. Because this one approaches the x-axis so quickly, even going out to 10,000 is going to break it. If we go out to 1,000, that's about all it can handle. So, with those two values that we have, what do you estimate the integral now is from 1 to infinity of e to the negative x? Based upon our numeric evidence, 0.367, right? The numeric evidence says 0.0 or 0.367. But how is that possible if we go out further and further and further? Just like with 1 over x, doesn't matter how far out we go, we can always zoom in and we can find more and more area to add. So how can an unbounded region, a region that is infinitely large, have essentially a finite area? Yeah, because what is being added is so small, it is so insignificant, it is essentially not contributing anymore to the area. So when we say the integral equals that, we're saying really that the area is approaching 0.367. There's a limiting value now. So here's kind of like the first contradictory idea. We have an infinitely large, that is unbounded region that essentially has a finite area, right? Go to Sherwin-Williams and say, I've got this huge space I need to paint. Well, how big is it? It's infinitely large, right? I could put cows in there all day long and they'll never run out of room. But I'm not a rancher, I'm a painter. So I need enough paint to cover 0.367, let's call it 0.368. I don't want to run out, square inches, and I'm going to go ahead and paint it. He goes, are you going to come back for more after that? No, that's going to be enough. I thought you said it was an infinitely large, unbounded region. It is, and that's enough paint to cover it? Yep. I'll probably even have 100th left over. Can I bring that back for a refund? No. That's kind of weird, right? Why did I mention cows? Because cows are big. And for an infinitely large, unbounded region, we should be able to stick as many cows in there as we want. But we're going to be able to paint it with a finite amount of paint. That's kind of a contradictory thing. So what's weird is that visually, both graphs are doing the same thing. But on the first one, the area is getting infinitely large. And on the second one, it's not. It's approaching a finite number. So what's the difference? It's a matter of how fast the graph goes to the x-axis. The first one goes pretty lazily, so the area grows to infinity. The second one goes to the x-axis with purpose, right? With fortitude. And so it pinches it off. If you want to think about it that way, it's pinching it off a lot faster. So we're approaching a finite area. That's pretty cool. All right, so what makes an integral improper? One reason. It approaches infinity as an upper bound or a lower bound, or same thing, negative infinity, okay? That's what makes it improper. All right, so it says to sketch the graphs of these. We've already done that, okay? We've already done that. So let's just skip F. We'll just say C above. Sometimes I do get ahead of myself, right? Especially when I'm driving. Yeah, sometimes it's hard for me to get out of my own way. Why would these two integrals give such different results? We already said, right? One approaches 0 lazily. That's a great adverb. And the other with fortitude, right? Okay, we'll just say faster. There you go. So it's a matter of how fast it approaches 0. So now the question is, all right, is there a cutoff then? If we kind of go from 1 to infinity for all of those types of functions, like 1 over x squared, 1 over x cubed, there's a whole family of those, 1 over x to 100, and then all of your exponentials, e to the negative x, e to the negative 2x, e to the negative 3x. Is there a cutoff between approaching infinity and approaching a finite number? There should be, right? There should be a cutoff. Like, sorry, you're too lazy. You have an infinite amount of work. Oh, man, you have fortitude and purpose, right? Your work's going to be done eventually. All right, so now that that's got you irked, and maybe it doesn't have you irked, right? Maybe you're a placid personality, and you're like, that's cool. I'm chill with that. We're going to go ahead and look at this. How to deal with infinite intervals of integration. Okay, so if the integral from a to b of f of x exists for every b greater than a, okay, for every b greater than a, all of them, then we say that the integral from a to infinity is equal to the limit as b goes to infinity of the integral from a to b, all right, provided that the limit exists and is finite. So if we ever have an improper integral, if you ever see infinity as an upper limit of integration, what we're going to do is we're going to turn it into a two-step process. We're going to first evaluate the integral from a to b, like we normally would using the fundamental theorem of calculus, and then we're going to take the limit as b goes to infinity. Okay, that's how we handle it. And on a free response, on the AP exam, anytime you're evaluating an improper integral, and they do show up, your evaluation has to come from a limiting process. That's what the scoring guidelines say. So we're going to practice that. But then again, if it's a multiple choice question and you're not graded on notation, I'll show you an easier way to do that without having to formally write the limit as b goes to infinity. It works the same way on the bottom. And I'm going to skip all this, but if you have a negative infinity on the bottom, you're going to do the same thing. You're going to take the limit as b goes to negative infinity and then integrate from b to c. Okay? So, and then sometimes we might have from negative infinity to infinity, and we'll have to like split it up. And I'll show you how to do that. Okay, so example 2. We're going to evaluate these now using the limit process. We have 1 over x to the 3 halves. We just saw 1 over x to the first, right? It went to infinity. What's the exponent now? 3 halves is equivalent to 1.5. So that's bigger than 1. So this one should go to the x-axis what? Faster or slower than 1 over x? Should go faster. So now the question is, if 1 over x to the first was too lazy, went to infinity, is x to the 1.5 in the denominator, is that still considered lazy? Or is that fast enough to approach a finite value? And then we'll look at x to the 2th power, which is a little bit faster, goes to the x-axis faster, and then 1 to the 3rd power, and that's a little bit faster yet. Okay? So let's go for it. I see the integral from 1 to infinity, so let's go ahead and start by writing the limit as b, we'll just call it b, as b goes to infinity of the integral from 1 to b of x to the negative 3 halves. So that would be a possible first step. And I'm just using b arbitrarily. Okay, you could use a here if you want. All right, now we can focus on the integral. So remember, we haven't evaluated the limit, so we have to bring it down each time. By writing x to the negative 3 halves, it's a simple power rule, right? So we add 1 to negative 3 halves, and we get negative 1 half, right? Negative 1 half. And then instead of dividing by negative 1 half, we'll multiply it by its reciprocal, negative 2. And now we'll evaluate it from 1 to b. So good so far, so good? Okay, good. So still writing the limit there. The limit as b goes to infinity. Remember, my personal choice is to always leave the coefficients out front with a beefy bracket. Good excuse to draw a beefy bracket. So when I plug in a b now, it's b to the negative 1 half, which is the same as 1 over the square root of b. I'm just going to write it like that. Minus 1 to the negative 1 half, which is 1 over the square root of 1. Now, you don't have to do the next line, but I will. You could probably evaluate it right from there. That's going to be negative 2 times 1 over the square root of b minus 1. So remember, with the limit, you could actually bring the limit inside if you wanted, and you can write it specifically in front of the 1 over the square root of b. So as many variables as you have in your expression, you could just put the limit in front of each one of those. We did that earlier in the year. So now it's time to evaluate it. What happens to 1 over the square root of b as b goes to infinity? It approaches 0. Good. So now when I evaluate the limit, I don't need to write the limit anymore. That's just negative 2 times 0 minus 1. Yes, yes? I've replaced the highlighted blue stuff with the 0 because that is evaluating the limit. Well, now I can evaluate it. 0 minus 1 is negative 1. Negative 1 times 2 is 2. So what does that mean? Did this one go to the x-axis fast enough to equal a finite area, to approach a finite area? Apparently so, yeah. What we say is because the area never equals 2, it just gets closer and closer to 2, we say that the area, and it's not always the area, but in this case it is, the integral in general, we say it converges to 2. It's getting larger and larger and larger and larger, but like e to the negative x, by significantly less and less and less and less. So it's not going to contribute to an increase that approaches infinity. It's going to contribute to an increase that only gets us closer and closer and closer to 2. Okay? So now we have the answer. Somewhere between 1 over x to the first and 1 over x to the 1.5th, there is a cutoff, right? Because 1 over x to the first approaches infinity, which I'll give you that word. When it goes to infinity, we say that this one diverges. Diverges means gets infinitely large. It diverges to infinity. Whereas just increasing the exponent by a half unit in the denominator, we get something now that converges to a finite area. Okay, interesting. So when the exponent was 1.5, we converged to 2. All right, let's try it out again with the second one. I got 1 to infinity. I see it's improper. So my first step is to write it as the limit as b goes to infinity of the integral. And I'm going to go ahead and say it's x to the negative second, because we know we have to integrate it, from 1 to b. So this breaks it now into a two-step process again. Evaluate the integral, 1, and then step 2, evaluate the limit. We just have to write the limit each and every time. So integrating, I get x to the negative first, divided by negative 1 is times negative 1 from 1 to b. Next line, the limit as b goes to infinity. I'm keeping my negative 1 coefficient out front with the beefy bracket. B to the negative first, when I plug in, is 1 over b, minus 1 to the negative first is 1 over 1. Let's go ahead and evaluate it now. The limit as b goes to infinity of 1 over b, what does that approach? That also goes to 0. So I'm left with negative 0 minus 1, which is 1. So we say the area converges to 1. The integral is 1, the area converges to 1. That's a smaller number than 2. Is that reasonable? Yeah, because 1 over x squared goes to the x-axis a little bit faster than 1 over x to the 1.5, because 2 is bigger than 1.5. And if it's going to the x-axis faster, it should be a smaller region, right? It's steeper, so you have less area. We have less area, it's equal to 1. So when I'm going to call this, since they're all the same form, I'm going to call this the integral from 1 to infinity of 1 over x to the p, if you let me do that. P for what? Power. Yeah, p for the power. So let's go ahead and see, because we want to notice a pattern here. Maybe there is a pattern. When p is equal to 1.5, the integral, we'll say, equaled 2. And over here, when the power equaled 2, the integral was equal to 1. Okay, cool. Interesting. Let's look at the last one now. 1 to infinity of 1 over x cubed. If you look at the graph in the first quadrant from 1 to infinity, it's going to look pretty much like 1 over x, e to the negative x, 1 over x to the 1.5, 1 over x squared. Being x cubed, though, does it go to the x-axis faster or slower than 1 over x squared? Should be faster. So do you think it's going to converge to a finite number or go to infinity? It should converge, right? Yeah, if we know that something that goes to the x-axis slower converges, then anything that goes to the x-axis faster should also converge. And it should also converge to something what in relation to 1? Smaller, okay? So we're expecting this one to converge to a number less than 1. Now, I'm going to do this one multiple choice style, okay? It's a little bit faster. If it's a free response, you have to write the limit. No big deal, right? Just a little bit more formality. If it's a multiple choice and you're not getting deducted for your notation, here's how we could do it. I'm still going to rewrite it as x to the negative third, but I'm not going to write the limit up front. Just leave infinity as the upper bound. Integrating, x to the negative 3 plus 1 is negative 2th power. And then instead of dividing by negative 2, I'll multiply by a negative 1/2. And I'll just evaluate it from 1 to infinity. Keeping my negative 1/2 coefficient out front, beefy bracket. Plugging in, I get infinity to the negative second. Well, that's the same as 1 over infinity squared minus 1 to the negative second is 1 over 1 squared. Now, here's why we don't really need the limit. We know that 1 over infinity squared is approaching what? It's going to 0. We know that because we know that having an infinity really doesn't mean we're evaluating it at infinity. Infinity is not a number. We just know that the bottom is getting bigger and bigger and bigger and bigger squared, and the top's always a 1. So now we can just evaluate it. Negative 1/2 0 minus 1 is -1. We end up with 1/2. So that's how you would do it multiple choice style. You don't have to worry about the limit. Free response style, if you did it this way, and you actually have 1 over infinity squared, you're going to lose a point. It has to come from a limit process, so it needs to be shown. This is like mathematical slang, right? So even though it's an improper integral, you might say, well, if it's improper, can't we use slang? No, right? Even when curse words are allowed, some curse words are not, right? Like you could say, like the brick wall that stops water, that's called a dam. You could say that on TV, but you can't say the F word on TV, right? If you say factor, that's totally different, right? Good. So let's go ahead and see if we can see the pattern now. When P, I didn't mean to write with highlighter, when P was equal to 3, when the power in the denominator was 3, the integral equaled 1/2. Does anyone see a pattern there? 1.5 became 2, 2 became 1. What's that? The integral is decreasing by a half unit each time? Well, here it increased by a half unit. As you go to a larger and larger power, the integral is getting smaller, right? Smaller. Does anyone see a relation betwixt the P and the integral? That one's a little harder to see. It's a little harder to see. But believe it or not, there is a pattern, okay? So fact. Ooh, I like facts, right? You can go on Jeopardy with facts. Or, I haven't tried it yet, but HQ, right, the app? Every day at 8 and 2. I need to try that. If A is greater than 0, okay, we've been using 1, but as long as it's greater than 0, you're to the right of the vertical asymptote. It could be 1/2, it could be 5, whatever. As long as you're starting at something greater than 0, then the integral from that positive number to infinity of anything of the form 1 over x to the pth power, okay? That's like p to the first, p to the second, p to the third. We say it's convergent if p is greater than 1. What does convergent mean? It means that the integral is going to approach a finite number, like we've been showing. If p is greater than 1, strictly greater than 1, it's going to converge, and it diverges, which means it's going to get infinitely large if p is less than or equal to 1. So what does that mean? That means we now have our cutoff. 1 over x to the first. The first one we met, he's the gatekeeper. Okay, anything that grows faster than 1 over x, like even 1 over x to the 1.1 or 1 over x to the 1.00001, those do go to the x-axis fast enough to converge to a finite number. It might be a huge number, but it's finite. If it's 1 over x to the first or smaller, like 1 over x to the 1/2, 1 over the square root of x, now those are going to go to the x-axis so slowly that they diverge to infinity. All right? So these are called P-series integrals. P-series integrals. P stands for what? Power. Good. Now, this is kind of appropriate. If we're calling those P-series, it's appropriate that the convergent and divergence of these P-series depends upon number 1, right? They're P-series, and they depend on number 1. They're P-series, and they depend on the number 1. Got it? Yeah, yeah. Not the number 2. These aren't called D-series. They're P-series. P for P, not P for poop. Okay, number 1. Equal to 1 or smaller, it does what? I'm sorry, scatological humor, I should just never go there. But y'all are young adults. I'm not saying anything Donald Trump wouldn't say. Less than or equal to 1, what happens? Convergent, divergent? Divergent. 1 or smaller, between 0 and 1, divergent. Strictly greater than 1, convergent, okay? Convergent. Now, here's the pattern that I was hoping someone noticed, but it's really hard. If you actually start at 1, which is the ones we've been doing, we could have started at 1/2 or 1/5 or even at 100, and it still would have converged if the P was greater than 1. But if A is 1, if you're starting at 1 and P is greater than 1, meaning it converges, it's always going to converge to 1 over p minus 1. That almost is worth memorizing, because what it does is it saves you from having to integrate, which is not going to take you too incredibly long, but kind of important. So if you're starting at 1 and it's a convergent p series, it will always converge to 1 over p minus 1. Let's see. Here, we got an integral of 2. Is that equal to 1 over the power, which was 1.5 minus 1? Well, let's see. 1.5 minus 1 is 0.5, right, which is a half. 1 over a half is 2. It worked. Sweet. Same thing over here. We got an integral of 1. Is that the same as 1 over the power minus 1? That's 2 minus 1. That's 1 over 1, which is 1. Sweet, it works. And over here, we got an integral of a half. Is that the same as 1 over p minus 1 when the power is 3? 3 minus 1 is 2. 1 over 2 is what, Tyler? 0.5. Yeah, you can answer with your thumb if you want, unless it's busy doing something else. Okay, yeah, 0.5, 1 half. Yeah. Remember, I had this rule at the beginning of the year, right? No cell phone. So if it's important, you may step out and make a phone call. I know how important it can be. I won't take your phone up there. Okay. So there you go. If it's a convergent p series, which means it's going from now 1 to infinity, 1 over x to the p, it converges to 1 over p minus 1. All right, let's take a stand, and then we're going to do a couple more. Example 3. It's going to be okay. To the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Honor the Texas flag. I pledge allegiance to the Texas, one state under God, one and indivisible. I'm just going to assume you were like typing in on your calculator with your thumb under the desk. Yeah. Thank you, Texas. Your worksheet's due when? Tomorrow? The last one on the key, I was lazy. I thought it was the same as the one from the notes, so I just pasted it in there. It's not. So I'm redoing the last one on the key. It's actually the 2016 BC4 question. So if you get to it before I post the correction, just go to College Board and look up the scoring guidelines, and you can see the correct answer. Okay? But I'll fix it. It requires L'Hopital's rule twice. All right, while you listen to Ms. Shriver, go ahead and take a look at this. Does it converge or diverge? While you're listening.
Tuesday, March the 6th. And look for our lunch visitors. Tuesday, also Texas A&M University San Antonio, and Thursday, New Mexico Military Institute. Today kicks off the National School Breakfast Week. Come eat breakfast in our cafeteria starting this week and receive a raffle ticket. Winners will be announced daily. Some of the prizes include smartphone cases, selfie sticks, and beach towels. And it's at least 600
beach towels.
Eat breakfast this Thursday the 8th. 2 prom tickets will be raffled off on Friday.
Anyone ever dried off a beach?
We got a raffle ticket this
you need a lot of towels.
The winner is 485-3464. That's 485-3464. You have until C lunch to claim your prize. Students, if your number was not called, please hold on to those coupons in case that prize is not claimed. We will announce another number for tomorrow. So hold on to your raffle ticket. Thank you.
6424, but the only number that matters to us right now is 2/3, right? So this is a P series because you have 1 over x to the power of P. We're starting at 1. So that's the important number, right? So now, without even having to evaluate it, since P, the power, is 2/3, which is less than or equal to 1, we know that it's going to grow infinitely large. So you can say the limit equals infinity or you could say it diverges to infinity. So if this were a multiple choice question, it might have like, there's only 4 answer choices now. So 3 of the answer choices might be numeric, and answer choice 4 might say diverges. Okay? That means the same thing as gets infinitely large or infinitely small. All right, all kinds of wonderful things in the recording today. Hello, this is Scorpy. Yeah, I will. I sure will. Andy, you're leaving prematurely. They want you to check out at the attendance office. Okay, how about this? 1 over x to the 1.1 power from 1 to infinity. Converges or diverges? Converges, right? P equals 1.1, which is greater than 1. So this one converges. Now, if it converges, it converges to a finite number. We need to know what that number is. Do we have to integrate it to find it out? Nope. It's 1 over P minus 1. What is P? 1.1. So on a free response, you could stop right there. But on a multiple choice, not. So that's 1 over 0.1. 0.1, what's the correct way to say 0.1? 1/10. So 1 over 1/10 is 10. So yeah, it's a pretty large area, right? But it does converge. It converges to 10. All right, how about this? 1 to infinity of x to the negative 7. Oh, I don't really recognize that. Let me rewrite it. Ha-ha, now I see the P series. See you, Andy. Converges or diverges? Converges, okay? And the reason is P equals 7, which is strictly greater than 1. And so now we know it converges, we can figure out to what it converges. 1 over P minus 1, where P is 7, so it converges to 1/6. Yeah. So these are worth recognizing. These show up a lot, and later on when we talk about infinite series, we'll have P series as well, which are closely related to these. All right, finally the last one here. We got 3 times x to the negative 3 halves. We're going from 1 to infinity, so that's the first thing you spy. Hey, that's an improper integral. If you bring the 3 out front, and then you rewrite that as 1 over x to the 3 halves, now it fits the form, right? Converges or diverges? This converges, all right? This one converges to, well, 3 goes along for the ride. Yeah, he's just a rider. So now it's times 1 over P minus 1. Not 1 minus P, P minus 1. That should be a positive number. And P is 1.5. So we've already done that one, but just to review, 1.5 minus 1 is a half. The reciprocal of a half is 2. 2 times 3 is 6. Yeah. So constant multiples do not help a function go to the x-axis fast enough. 3 makes it a little bit steeper, which wouldn't help. But if it were like a 1/3, that would be a vertical compression by a factor of 3. If it were 1/10, that would be a vertical compression by a factor of 10. That's not going to do anything to help one that doesn't converge on its own with the power. It's not going to help it compress it enough to make it go fast enough, unfortunately. Okay, so it's all about the power on x in this form. Okay, that's a good place to stop. Any questions? All right, now you can text your loved ones your new knowledge. Yep. Hang on, just a second. Let me